So we are generating these Taylor series or Maclaurin series by differentiating to find the derivatives and then using the theorem 1 to calculate the values of our coefficients an. And the Maclaurin series is just a special case of Taylor polynomials where the center is not at some number, but at the center is at 0. So c equals 0. So we're going to construct a Maclaurin series for ln of 1 plus x. And again, to do this, we are going to start by working out the derivatives. So we're going to start with log 1 plus x. We're going to evaluate it at the center 0, so we get log 1, which is 0, which gives us a coefficient of 0. Our next derivative is going to give us 1 over 1 plus x. We're going to evaluate this at 0, so we're going to end up with 1, and then our an is going to be 1 over 1 factorial, which is just 1. And differentiating this, we're going to have our negative 1 power, so we're going to end up with negative 1 over 1 plus x, and we go from power negative 1 to negative 2. Evaluating this at 0, we plug in 0, we get negative 1, and our coefficient then becomes negative 1 over 2 factorial, which works out to be 1 over 2. So we're going to multiply by negative 2 to get positive 2. We're going to decrease the power by 1, so we get 1 plus x to the power negative 3. We evaluate our derivative at x equals 0. We're going to get positive 2. So we end up with positive 2 over 3 factorial. That's going to work out to 1 over 3 as our coefficient. So we've been also asked to find the pattern in the coefficients of an, and we need this pattern to be able to come up with the series formula for this as well. So if we want to put this in sigma notation, we're going to need to come up with this pattern. And this pattern is actually quite hard to find in a lot of cases, but in this case, we're going to see if we can come up with this pattern. So continuing on with my derivatives, I'm going to multiply by negative 3, so I get negative 6, 1 plus x to the power 4. We're plugging in, evaluating this at 0, I'm going to end up with negative 6. So I end up with negative 6 over 4 factorial. That works out to be negative 1 over 4. Again, I need to make sure I have my negatives here because you can see that there's a pattern emerging here. It's going from plus, minus, and so we could probably expect this to be alternating, so this is likely going to be plus. And when we actually work out that next derivative, we get positive 24 over 1 plus x to the power of 5. This becomes positive 24. So we end up with 24 over 5 factorial, which is 120. And this simplifies to 1 over 5. Okay, so we can see that there seems to be a pattern showing up for our an. So I'm going to maybe see if we can come up with our formula. So we can say that our Taylor polynomial is going to be in sigma notation. Again, this is hard to write it in sigma notation. And we need to find this pattern of coefficients for an. But since we can probably figure out that pattern, we're going to write this in sigma notation. Starting at n equals 0, we have an infinite number of terms. This is an alternating series. So I'm going to go negative 1 to the power. In this case, we're going to start with negative, positive. So our odd powers are going to be positive. So I'm going to do n plus 1. That's going to alternate our series. And it looks like the denominators just are represented in the n value. So it's going to be n. And then the power series part And since this is a Maclaurin series, it's just going to be x to the power of n. So there it is. There is our sigma form of this. If I want to write this out, and I'm going to write my Taylor expansion for 5, my 5th degree Taylor expansion for this. This is going to be 0 plus 1x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the power 4 plus 1/5 x to the power 5. Okay, so I'm just going to maybe squeeze this in a bit. Actually, I'll just leave it like that. And so this represents our Taylor polynomial. I'm going to just simplify this out a little bit. So we're going to have x minus x squared over 2 plus x cubed over 3 minus x4 over 4 plus x to the power 5 over 5. So this represents our Taylor expansion. Because we could come up with the formula for the coefficients, we can write it in the sigma form. Now we're going to use the 4th degree Taylor polynomial to estimate log 2. So what's this going to look like? So I'm going to say that log 2, or log of 1 plus, and we're substituting in 2 into our log 1 plus x function, is going to be approximately equal to our Taylor polynomial of 4th degree when we plug in, that's going to be log 2 is going to be when we plug in 1. So when we plug in our x equals 1 into our Taylor polynomial, this is going to give us our approximation. So looking at our Taylor polynomial, it's going to be 1 plus 1 squared over 2 minus 1 cubed over 3 plus 1 to the power 4 over 4. That represents our 4th degree Taylor polynomial. And when we work that out, we're going to end up with 0.5833. Okay, so this represents an estimation of log 2. So we're saying that log 2 is going to be approximately equal to that. Now, when we compare to the actual value of log 2 from our calculator, our calculator value for log 2 works out to be 0.69314 ... Okay, and you can see that there's actually quite a bit of error here, because if you think about where our center lied, our center was at c equals 0, and we're evaluating at x equals 1. So there's going to be a fair degree of error because we are actually quite far from the center.